right, everyone. Welcome to the second 2024 office hours. It's been a bit of a crazy start to the year, so I haven't had these quite as regularly as I normally do, but some of you may have seen me in Los Angeles at the Academy Museum, the Twister viewing and that conversation afterward. That was something I very much enjoyed. That series, by the way, of disaster films at the museum with scientists speaking afterward is continuing for the next few weeks, so there are other opportunities to watch other films and listen to other scientists talk afterward if you're interested. What we're seeing right now is not necessarily what I expected to be seeing at this point in this particular winter season. I'll discuss a little bit of where we are, some interesting short-term weather, not just in California, but across the broader West, and what the seasonal predictions are saying now, a bit different than what they were saying just a few weeks ago. So we'll talk about that. And then also, 2023 was now officially the warmest year on record by a considerable margin. And that's, of course, been in the news a lot, justifiably so. But I did want to talk about the broader context of that and what it means and also what it doesn't mean, because there's a lot of misinterpretation going around that acts both to exaggerate but also understate the magnitude in different ways of what we're seeing all around us. So I did want to offer some thoughts on that as well. So starting with the short-term weather, right now there is a massive Arctic air mass building up across Western Canada and the Pacific Northwest. All of this is going to move southeastward and make it quite far south east of the Rockies. So it may make it as far south as central and even South Texas, as these cold Arctic air masses sometimes tend to do, as they dive much farther south on the eastern flank of the Rockies than they ever make it on the western side. So South Texas, for example, can see much more extremely cold temperatures than Southern California due to the geography of the continent of North America. That extremely cold Arctic air, if it makes a beeline from central or interior northwestern Canada all the way to South Texas, if it just takes that overland trajectory from northwest to southeast, it doesn't go over any water. So even though South Texas is similar to or even further south, a lower latitude than Southern California, what we end up seeing is that it's still more susceptible to extreme cold than Southern California, because for California, there really are very few options for unmodified extremely cold Arctic air masses to make it all the way to the coastal southern part of the state, especially because almost any air mass that comes here is going to have made some overwater trajectory, thereby becoming at best a modified Arctic air mass. So California is probably not going to be extremely cold. This is definitely a cold period, and there's some cold overnights right now, but nothing record-breaking or earth-shattering. The cold will be much more extreme along the Rocky Mountain Front Range eastward into the center of the country and parts of the Northeast, and there will be multiple severe winter storms all lined up. One affecting the Pacific Northwest, probably from about Portland southward into southern Oregon. So even sea level in Oregon will see anything from an ice storm to a heavy snowstorm, and even localized blizzard conditions in the Columbia River Gorge, again near sea level, where snow will fall all the way down to the bottom of the gorge, along with outflow winds of 50 or 60 miles an hour. So that sounds like pretty nasty weather. And then back-to-back blizzards in the Midwest and in some parts of the East, including some potential for historic blizzard even in places that are fairly accustomed to blizzards this time of year, including Chicago, with very heavy snow and very strong winds possible. All of this because of a highly amplified blocking pattern in the Arctic. So there's been a big ridge of high pressure near Greenland and another one elsewhere in the other side of the Arctic that has essentially displaced a lot of the Arctic air to the upper mid-latitude. So the Arctic right now is much warmer than usual, precisely because the whole cold air mass that develops up there this time of year has been displaced out of the Arctic and into the mid-latitudes. And that is that air mass that's going to make it over the central part of North America later this week and is brushing the Pacific Northwest, interacting with some Pacific storms to deliver a pretty major snow or ice storm to someone in the Pacific Northwest. It originally looked like it might be Seattle. Now it looks like it might be Portland or even Central Oregon, south of Portland. Portland might be on the northern fringe even. At the same time, this storm is going to strengthen as it approaches the coast, and it looks like it's going to take a slightly more southerly trajectory than had been previously the case, meaning that the European model versus the American model, the European model's southern track for the system is winning out, which means this will be a more significant storm for Northern California Friday into Saturday, especially. With widespread heavy rainfall, strong winds along the north coast, extending southward maybe as far south as the I-80 corridor. So parts of the Bay Area and the northern central Sierra could also get hit by a pretty major storm Friday into Saturday. Again, a lot of rain, a lot of wind, and reasonably low snow levels. Nothing extremely low, but this will be a snowpack builder, especially for the central and northern Sierra, which is good news. We need it. Snowpack is below 50% of average for the date still, despite recent storms, so that will generally be good news. This storm could bring some minor flooding even up on the north coast and some other spots in Northern California, but overall, and also major travel difficulties, really from the north of the Bay Area, essentially, and in the mountains for sure, where some blizzard conditions will be expected. But this won't be a huge storm for Central or Southern California. In fact, it really will be mostly a light shower and wind event south of there. Not a big rainmaker, unfortunately. But this will be a considerable storm, and there could be some flooding, especially along the north coast, and especially if the European model ends up being correct. This pattern is this blocky pattern, this highly amplified meridional pattern, is not necessarily the kind of pattern we see especially often during strong El Nino years. It doesn't mean they can't happen. It just means that El Nino tends to favor strong zonal jets, which is essentially the opposite of a strongly meridional pattern. So this isn't that. And the other thing is that it really doesn't look like it's going to last that long. So this highly amplified meridional pattern with lots of Arctic blocking looks like it will slowly fall apart over the next week or so, and a more zonal pattern may reemerge. Unfortunately, though, for California, this zonal pattern generally in the northern hemisphere may not translate to a more active storm pattern. In fact, right now, there's some indication of a ridge that may build in even more strongly in about 7 to 10 days, bringing a period of drier and more noticeably warmer weather once again. So this brief colder interlude might quickly return back toward warm, and probably not especially wet, at least through January 20th or so. Thereafter remains to be seen. There might be some more active MJO or Madden-Julian oscillation activity that does a better job matching up or syncing up with El Nino's forcing. El Nino, by the way, still there and cranking, but probably on its last legs. It's a strong to very strong event presently, but there's a lot of consensus in the multi-model ensembling that it will start to rapidly weaken at some point in the next month or so, essentially ceasing to exist by spring and more likely than not transitioning towards significant La Nina conditions, so cool temperatures in the eastern tropical Pacific Ocean once again by this summer. So we still have El Nino. It's still with us. The influence of El Nino will likely be with us the rest of winter, but probably not much longer than that. Then there's the question of what the influence has actually been this winter, because this has not been as wet of a winter in central and southern California, at least so far, as some might have hoped or expected, including what was the tilt in the odd towards wetter conditions in the seasonal prediction. Now, it is important to remember, and I've emphasized this over and over again, that the main period of El Nino's influence on California precipitation is January through March. It's currently January 11th, so technically we've only had 11 days in that window, that January through March window, where El Nino's influence is most pronounced in California. So it is not very strong in December, and it's nearly absent up through November. So we shouldn't perhaps be too surprised what's happened so far, but in general, as we're heading into January, the pattern right now also doesn't look very El Nino-like, and that is frustrating. Also frustrating is the fact that the most recent round of seasonal predictions from the modeling centers around the world now have removed that tilt in the odds towards wetter than average conditions for the rest of January, February, and March. That is pretty conspicuous. That's not really what we were expecting to see at this point. What I will say is that all seasonal predictions, again, just to reemphasize, are always tilting the odds. So we're not talking about certainties. We're not talking about being able to be very specific about what the influences are. And the reason for this is really pretty simple. El Nino is but one of many factors that matter in terms of what happens during California winter. But the reason why we keep perseverating about it, we keep harping on this, is because it is really the only one that we can predict with much skill. And so it's not to say that the other factors aren't important, but it's to say that we can't predict them several months in advance. And this year, essentially, I think what we probably should be thinking about is the El Nino prediction was correct. Prediction was for a strong to very strong El Nino peaking midwinter. That's exactly what happened, once again. But California has not had really wet conditions yet. So what that means is that something else in the system has been disrupting that influence. It does not mean that El Nino's influence isn't there or isn't important, but it means that something else is actively counteracting it. And so far this year, there have been some weird things that have happened. There have been some unexpected sort of variations in the Madden-Julian oscillation where it kind of looked like it was going to take off and extend and do its thing, and then it kind of got stalled. The MJO propagates, sort of circumnavigates the globe in a longitudinal sense. And what you need to see is high amplitude of that pattern, but also enough progression at the right rate. So everything about that pattern matters. How the amplitude of the MJO wave signal, how quickly it propagates longitudinally. If it's too fast, it doesn't really get a chance to phase lock, and so it kind of just it doesn't exert much of an influence. If it's too slow, then it can fade away. You kind of need that Goldilocks of a strong enough signal that's propagating at the sort of a moderate speed to sync up with the seasonal forcing from El Nino, and so far we haven't seen that. We might still see that later this winter. Our MJO predictions also leave a lot to be desired. And so we don't know yet when or if that's going to happen. If it does, that's when I would expect to see the big storm cycles in California this winter, and they could be quite big and quite wet and quite warm still. I mean, it's still early January. We can see storms like that certainly in January, but also in February and also in March very easily. In fact, I still think this year will hinge mostly on what happens in February and March in California. Long talked about how this year was likely to be a back-weighted season. Now that's even more true, but now the question is it sufficiently back-weighted to make up for the fact that December and January don't look like great months in most places. There are a few caveats. The Central Coast, for example, did end up wetter than average in December, and a lot of that is because of that extremely wet cutoff low that brought this slow-moving atmospheric river and just hour after hour of torrential thunderstorm activity that led to one of the heaviest hourly rainfall rates on record in Ventura County, and that may be one of the heaviest rainfall rates on record for a non-mountain part of California that I can recall at any point. Over 3 inches in a single hour, right near the coast, is a whole lot of water, and that caused a lot of flooding locally. That did not, fortunately, extend over the whole state, but it did mean that that storm plus a couple of others, the Central Coast is sitting pretty so far, even though coastal Southern California from about Orange County southward into San Diego County, as well as the Sierra Nevada, are not doing so well. The North Coast and the Bay Area and big parts of the Central Valley are doing okay. They're ranging anywhere from slightly below to slightly above average this season. But the real losers so far, precipitation-wise, have been the Sierra Nevada and far southern coastal California, so Orange and San Diego counties specifically. Everyone else has been doing a bit better. The mountains, the Sierra Nevada, the snowpack deficit was amplified by the fact that December was near to record warm in some parts of California. In fact, December was the warmest December on record for 2 of California's climate divisions, the Central Coast and the San Joaquin Valley. And everywhere else in California, it was a much warmer than average December, and in those 2 particular divisions, it was singularly the warmest December on record. And that means that snowpack has been degraded not only because of the lack of precipitation so far this season, but also because this has been warm. Some of the precipitation that fell in December fell as rain, even at high elevations. And so By the way, there's it looks like there's some trolls in the comments here. Please just flag and move on. It's not super easy for me to uh, moderate in real time, but I will when I go through and look at the questions a little bit later for the Q&A portion. I will take care of that accordingly. So the Sierra Nevada snowpack is still in most cases under 50% of average. In some cases, it's only only 25% of average, despite the fact that it has been snowing recently. And this is I'm not an avalanche expert, but this is likely has at least something to do with the tragedy yesterday at Palisades, where there was an inbound avalanche that even folks were not well outside of bounds, but this is within the primary area of the resort that did kill at least one person. And a lot of folks have been reporting to me. In fact, some folks even sent me images. You can see this. Be careful if you do this because you very well might trigger an avalanche. There have been a lot of other non-fatal avalanches in the last 48 hours. But folks have shown me photographs of a really degraded or rotten snow layer right at the base. I mean, the base being almost right at ground level, with a much larger slab of more recent, colder, powdery snow on top of it. That's a recipe for really pretty significant snowpack slab failures on steeper slopes. So unfortunately, that's probably what happened there. And this is a fairly unusual condition because it requires a really poor, warm, low-quality, thin snowpack for the first portion of the season, followed suddenly by a much colder, fluffier snow right on top of it. And although there's not a huge amount of snow on the ground, it's clearly enough to cause large snow slides in the right conditions. Somebody was telling me earlier that there was another avalanche today at Mammoth, another inbounds avalanche, although this one didn't, I don't think it affected people. I think it occurred early in the morning. So clearly this is an issue. This does have to do with the quality of the snowpack and how warm and dry December were, because that helped create that really low quality rotten snow layer right at the base. And again, I don't know that that's going to go anywhere because that's the base is the base is the base. So again, I'm not a snow or avalanche expert in that sense, but there is enough evidence that these antecedent climate conditions, the record warmth and the unusually low snowpack to start the season, followed by this sudden transition to colder, powdery snow, probably played a role there. Let's see what else is going on. Yeah, the rest of the country, extreme cold in the center of the country, blizzards anywhere from the Columbia River Gorge, the Washington-Oregon border, Chicago, the place where you might expect to see a blizzard in January, and a big snowstorm in the interior Northeast as well. Major storm surges along the eastern seaboard. In fact, cities like Philadelphia and Portland, Maine, the other Portland, I believe, have seen record-breaking coastal flooding. So the highest tide levels ever recorded in these areas. And some of these places have tide records going back a couple hundred years because these are some of the older cities in the United States. So it is notable that these places have seen their greatest storm surges and highest tides on record. This is not a tropical hurricane, but a winter storm. The problem is it occurred during high tides. High tides are a lot higher on the eastern seaboard than they used to be due to sea level rise and global warming. So the storms themselves have been particularly intense, but then on top you add a rising sea level on top of it, and you get record-breaking coastal flooding and pretty damaging coastal storm surges. I mean, there's a lot of damage with some dramatic footage coming out of major deep flooding in some of these East Coast cities the coastal cities from the storm activity. In the same year, when some places in the Northeast still haven't seen a heavy accumulating snowfall in several years. You've gone several winters now without that in some spots. So really just kind of an extraordinary sequence of events. California right now is, again, in probably the least weather active part of the country right now. And that's saying something because it's quite active elsewhere. Friday, Saturday, it'll become a lot more active in Northern California, but still probably not extreme storm activity. And then Southern California, other than light showers and gusty wind, not much on the horizon right now. Uh, One thought about why the seasonal models have recently shifted towards drier conditions for February and March, somewhat contrary to strong El Nino predictions. Granted, there's not a very strong dry signal. It's really just drier in relative terms to the tilt in the odds towards wet conditions that we saw earlier in these same models for those months. Uh, they're very slightly tilting on the dry side of neutral, but not in a statistically significant way. What that's really telling us is that there's about equal odds of above, below, or near average precipitation in much of California for February and March and April. That doesn't mean that precipitation is going to be near average. It just means that there isn't actually a very strong signal in terms of what the models can predict about what might happen next. And it may mean that they're missing something. It may mean that they're a little bit overly sensitive to the initial conditions. And in some conversations I've had with folks recently, they suspect that this shift might be because they were initialized during a phase when the Madden-Julian oscillation was really unfavorable for California storms. And sometimes they're known to be a little bit overly sensitive to those initial conditions. So if the Madden-Julian oscillation does in fact improve and starts propagating at the right speed and amplitude, we may not end up seeing those near to below average precipitation conditions over the next couple of months. It could end up being quite wet if El Nino syncs up with that MJO while El Nino is still exerting an influence for the next couple of months. But I think what this tells us is that this is a really difficult year to do prediction, that the record warmth of the non-tropical global oceans currently is still wreaking havoc with understanding our patterns. And, there will be questions about whether this year is instructive or not in terms of what might happen in a warming climate with strong El Niños to come, and what that influence might be for California weather. I don't think we know at this point. A lot of folks just make the assumption that El Nino doesn't matter anymore, and I still don't think that's true. I just think that there are other things going on that we're not capturing correctly. So the El Nino influence, I think, is still there, but perhaps the propensity for that influence to be outweighed by other things that are changing more, that I think is a possibility. We don't know yet. This is a very active area of climate science. May have more to say about it in 6 to 12 months. That's sort of the usual time scale of publication in this world. And I will say that this transition towards potentially significant La Nina conditions next summer is somewhat striking, because these same models project that the mid-latitude oceans will stay near to above record warmth with La Nina conditions, and then that'll be yet another oceanic configuration globally that we've never seen before. One thing that really jumps out is the likelihood that could create a very high risk of a lot of Atlantic hurricanes next year. So that's something to watch for Gulf and East Coasters out there. For California, it really depends what happens next fall and winter, which is really just too early to be talking about right now. We're still talking about the present winter, so. All right, I'm going to take a quick sip of water, and then I want to turn to 2023 record global temperatures. All right, so what we've got really is, sorry, I'm just changing a couple of settings there. Okay, sorry, back to it. So as many of you probably have read already in the news or seen on TV, 2023 was the record warmest year since for really the period we've been keeping temperature records on Earth. And in terms of reliable global temperatures that we can measure with monthly to annual granularity at global scale, that goes back about 125 or so, 130 years. So over a century of record keeping. I think it's safe to say that 2023 was the warmest year in well over a century of record keeping, and in all likelihood a lot longer than that. We just don't have direct instrumental temperature records with sufficient temporal or spatial granularity to let us know that for sure, going back hundreds or thousands of years. Now, we do have that information if we do multi-year or multi-decadal averaging. We can say that the last couple of decades probably are the warmest in thousands of years from the paleoclimate record But that paleoclimate record globally doesn't always allow us to see what the temperatures were in individual years. You kind of have to squint a little bit and average smooth over multiple years and decades. And so we know that the rise in Earth's temperature in a decadal and centennial context is extraordinary in thousands of years, but the most accurate quantitative statement we can make about 2023 is it's the warmest year in well over a century of record keeping, because that's the period for which we have the kind of records to make an apples to apples comparison. It's not, of course, surprising that 2023 is record warm. We would expect to see progressively more and more record warm years due to global warming. In fact, we would expect to see a new record every few years. Generally speaking, we expect to see new records as we stair step up to a warmer climate during significant El Nino years. And so that's exactly what we've seen this year. And this is a question I've gotten a lot from journalists, and I think it's important to differentiate. There's really two questions here. One is, why is 2023 so much warmer than 2022? There was a big jump in temperature and just year to year from last year to the most recent year. And then there's a separate question of, why is 2023 nearly 1.5 degrees centigrade above the long-term baseline? And I'll answer the second question first because it's easier. The reason why 2023 is so warm overall is 80 to 90% due to global warming. That gets us 80 to 90% of the way there. That gets us to 1.3, 1.4 degrees centigrade out of about 1.5 degree centigrade above the long-term average. So that's most of it right there. That's just what the long-term trend is. And so that part of it is pretty much unavoidable, inexorable reality. But that other 0.1 to 0.2 degrees this past year was a little bit surprising. It's a pretty big number, and it means that the total number is, depending on which data set you use, pretty darn close to 1.5 degrees centigrade above the long-term pre-industrial average temperature on Earth. That's a pretty big number in a global climate context. It may not sound like it, but it truly is. And the reason why this year was so much warmer than last year, well, the main reason is that last year was a strong La Nina event, and this year is a strong El Nino event. So that probably right there explains at least 0.1 degrees and maybe up to 0.2 degrees. So if you ask the question of why is 2023 so warm, the number one answer is global warming. Why is 2023 so much warmer than 2022, though? It's not like global warming suddenly got a lot worse between last year and this year, so the answer really there for the year-to-year jump is probably mainly El Nino. And so if you add those two things together, the long-term warming plus El Nino this year, and in particular the transition between La Nina to El Nino, you almost get the top-line number that you're looking for. Now, there are some other things that happened this year, and the second half of 2023 was really kind of shockingly warm. In some cases, there were weeks well above 1.5 degrees centigrade above average, and that does give some scientists pause. There really was something pretty remarkable going on globally during the second half of 2023 that made it way, way warmer than anything else we've seen. The global oceans were just, they were cooking. The atmosphere just was warmer, just so much warmer, just record-shattering in many cases warmth. I don't think we have a great understanding of exactly why the second half of 2023 was so darn hot, globally speaking. And so I'm not totally convinced that that can just be blamed on El Nino, although that is a big part of it in terms of the global number. It doesn't really explain the regional heat waves or the extreme regional oceanic warmth either. So there is probably something else going on there. Now, is it necessarily a sign of, something that is going haywire in the climate system, or something that's alarming, or something that's, more importantly, going to persist moving forward? I don't really see a lot of evidence that that's the case. Sometimes we get these spikes, and it's kind of just due to a bunch of tiny or not so tiny things that kind of randomly align, depending on whether you call it lucky or unlucky, in a somewhat fortuitous way with other things. So we had long-term global warming, that's not going away. We had this big transition from La Nina to El Nino, that's largely random chance. And then we have all these other factors that may have aligned. They're small, but in aggregate maybe not quite so small, certainly not negligible, in a way that amplified the warming in 2023 even more. And Within this last category, I would include things like the Hungatonga eruption back last year that injected a bunch of water vapor into the stratosphere, some recent changes in aerosol emissions from different sources, including ships. At this point, the evidence implicating the volcanic eruption or ship aerosols is not very strong. It's not that these things don't affect climate, it's just that the global influence is just not that large relative to these other things. So it's not to say that they aren't real or that they don't matter, especially at regional scales where they probably matter more than at global scales. But it's to say that really, big picture wise, the number one answer is global warming. The number two answer is this big transition from La Nina to El Nino. And the number three includes both some things we do know about, the volcano, the ship aerosols, and some other things, but maybe also some things we don't understand so well. And in there is always the potential for some unpleasant surprises. Wally Broker once said that the climate system is an angry beast and we're poking it with sticks. James Hansen has remarked on I believe it's a quote, the Faustian bargain, of the fact that as we start to clean up our air pollution from a smog and soot perspective, that kind of pollution has cooled the Earth, while greenhouse gas pollution has mainly outweighed it and warmed the Earth. Well, it looks like we're reducing our aerosol pollution faster than our greenhouse gas pollution, meaning that right now, although it's a net positive, I still think for humanity that we're reducing those aerosol pollution sources because it killed literally millions of people a year in terms of premature deaths. Breathing in that stuff is terrible for everybody. So it's good that we're getting rid of it, but the problem is the Faustian bargain, as Jim Hansen called it, essentially is that we are amplifying the rate of warming, not because the rate of warming itself is spontaneously accelerating, but because previously we were kind of driving with our foot on the accelerator and on the brake. Now our foot was more heavily on the accelerator than on the brake. But what we're now doing is our foot is still on the accelerator and we kind of just took our foot off the brake. So this is the challenge. The removal of these aerosols, that's what results in this Faustian bargain. It's a good thing that we're not, that collectively as a global society, that we're not breathing in as much of this aerosol pollution as we used to. Undoubtedly so. But the bargain is that now we're trading that off for a slightly accelerated rate of global warming. Now, I will say this was not unanticipated. Hansen has been talking about this for decades, and other scientists have quantified it more formally in recent years. It's been very clear this was going to happen. So just to be totally crystal clear, this is not something that was unanticipated or not. So this is baked into projections by the IPCC and climate models where the warming was expected to increase. The rate of warming's a little bit right around now as these aerosol emissions started to decrease, but greenhouse gas accumulations continued in the atmosphere. And that, I think, is part of also what we're seeing. And why there might have been a slight, it is slight, but it is mathematically perhaps there, acceleration in the rate of global warming in recent years. It's not dramatic, it's not runaway warming, and I think we probably understand it mainly because of this aerosol effect. It's not abrupt. It's not so much that there are a lot more aerosols this year than there were last year, but as generally speaking, as the years go on, we finally started to reverse this aerosol pollution, and we have not really meaningfully started to reduce the greenhouse gas pollution that has the opposite warming effect rather than the cooling effect of the aerosols. So that's the other thing that we're seeing right now. It's not so much like last year versus this year kind of difference, but it does explain why this decade perhaps we may be seeing slightly faster warming than some recent decades, although there's also just natural variations in that. So if you think about global warming, it's not just a straight line upward over time, it's kind of a wiggly upward line that, we call it stair stepping. And there was a bunch of scientific papers written about the quote unquote, the global warming pause back around 2010. Well, really what happened was it was a bunch of people writing a paper about a temporary period where there was relatively little warming because we were kind of on one of these flat parts of the staircase, and it lasted a little bit longer than some of the other periods that we've talked about in the past. But what happened after about 2015 is we then had another stair step up, and now we're having another one right now. So I fully anticipate, by the way, this is an official prediction by Daniel Swain, that there will be climate denial papers and publications and online comment sections arguments about the global warming pause circa 2025. Because this year we just shattered our previous record warmth, so meaning that the next couple of years are likely to not continue to shatter that recently set record. In fact, I would not be too surprised. 2024 is likely still to be very warm, similar to 2023, if not even a bit warmer. But 2025, highly likely 2025 will be cooler than either 2023 or 2024. And that's when these no net warming since 2023 claims will start to come out of the woodwork. Look, it's cooler in 2025 than it was in 2023. We got global cooling, right? Well, that's kind of like saying that we have global cooling because you measured the difference in temperature between noon and midnight and said that it got colder. It's true, but you're really missing the point and the bigger picture. So the other thing I wanted to talk about here is this notion about 1.5 degree warming. Now, I've talked before about how these specific numbers you hear about, 1.5, 2 degrees, 3 degrees centigrade of global mean warming relative to the pre-industrial era, that they're not truly thresholds. They're not well-defined geophysical cliffs, as I like to say, but they are political targets. So these are numbers that don't necessarily have any inherent physical meaning. So it's not like something necessarily goes haywire in the Earth system when we hit 1.5 versus 2. But on the other hand, it is true, though, that there are real tipping points in the Earth system. We're talking about sudden melting or loss of the continental ice sheets in Antarctica or Greenland that could cause rapid sea level rise, much faster than the current median predictions. Or die-offs of tropical rainforests, particularly the Amazon, in a self-perpetuating fashion, or of coral reefs, which we're already starting to see some evidence of that happening already, unfortunately, or even really big, bad, scary things like the North Atlantic overturning circulation. This is sort of the more scientific version of the quite exaggerated a day after tomorrow type scenario. That's a film, by the way, that's on the Beware the Elements series at the Academy Museum. I think Alex Hall is speaking after that one. But suffice it to say, that film does not accurately describe what the world would look like in the case of a slowing or even collapse of that system. On the other hand, it would be a truly cataclysmic global event. It just wouldn't look quite like that. Those are all things that could happen as we experience global warming, and the challenge is that we don't know, as Earth scientists, exactly where those tipping points lie. It's unlikely that most of them lie below 1.5 degrees centigrade of global mean warming, but it's not impossible that some of them do. The likelihood starts to rise considerably once we get above about 2 degrees of global mean warming, and by 3 degrees, it's quite likely that we will have hit at least one or two of these tipping points, which is kind of a scary thought, given that our current trajectory is towards about still around 2.5 degrees centigrade of global mean warming. That's very much in the territory that could trigger one or more of these tipping points. And it could be at 1.5, it could be at 3.5. And the problem is we don't know, and we may not know, except in retrospect. So most risk management in this kind of context would dictate prudence and caution and trying to rein in warming to the lowest possible level, because we don't know exactly where the dragons lie, but we are pretty sure there's dragons out there. The climate system is, as has been said, an angry beast. So the reason I bring up 1.5, though, is you may have noticed that I just brought up 1.5 in a different context earlier in the conversation, which is to say that this year, by some data sets, this was a 1.5 degree year above the long-term baseline. So doesn't that mean then that, well, we've already hit 1.5, so much for that as a target? Well, not exactly. The reason is that 1.5 defined in terms of tipping points or in terms of IPCC targets is actually a multi-year average of 1.5. So essentially it says at a point in time where the average amount of global warming over many years is about 1.5 degrees. What that means is that when we reach 1.5, according to that definition, there will be a lot of years that are well above 1.5 and still some years that are below it. It does not mean the very first year we reach 1.5. So in other words, the global average temperature increase on a multi-year basis at present is right around 1.35, maybe 1.4 degrees centigrade. That means we still have another 0.1 or 0.15 degrees centigrade until we get to 1.5 as defined in this context. So what that means is really there's two things. There's the good news and the bad news. The good news is this does not mean we've hit 1.5 early or earlier than expected. It means that we haven't actually hit it yet, according to that definition, at all. We still have some years to go, an additional tenth or two of a degree of warming to get to that point. That's the relatively good news. But the bad news is that what it means is that you ain't seen nothing yet. And 1.5, 1 year of 1.5 is not representative of the kinds of hazards that we're going to see, the kinds of extreme events that we will actually see in a 1.5 degree world as defined in the more comprehensive way, meaning that, you know, if you just do a simple fraction, what fraction of 1.5 is 1.35? That means we have another 10 or 15% of global warming to go before we get to 1.5, even accounting for this year. So take this year and then add another 10 or 15% to it in terms of the increase in the frequency and magnitude of extreme events, of extreme heat wave, of extreme downpours that we saw this year. And that is more like what a 1.5 degree world would look like. And then you can do the same exercise for a 2 degree world or a 3 degree world, and you paint a pretty alarming picture. So on the one hand, the good news is that we didn't suddenly breach this 1.5 degree target much earlier than expected. That would be really bad news because it would suggest that we're underestimating something in the rate of warming. We do not see that evidence at present. But the bad news is we are, in almost all plausible futures, going to hit and exceed 1.5. And so we're going to find out what that world looks like with an additional increase in extreme events and beyond. Unfortunately, we're still very likely to make it past 2 degrees centigrade. And there has been a lot of progress, don't get me wrong, on emissions relative to the trajectory that we were on just a decade ago. We were on a path towards 3 or 4 degrees of global mean warming this century with the kinds of policy implementation we had just 10 or 15 years ago. That's a really shocking number. It is now pretty likely that we're not going to see more than 3 degrees of warming this century. That's a pretty significant relative success. And the most likely amount of warming at this point on our current trajectory is closer to 2.5 degrees or even a little below, maybe more like 2.4 degrees centigrade. So relative to the path we are on, that's very good news. But in absolute terms, it's very bad news still because, as I've mentioned, 1.5 degrees of warming is already a big problem. 2 degrees is an even bigger problem, and 2.5 degrees, we really start to get into that territory where we may start to see our Earth system tipping points triggered. And that's still the path we're on. So, as usual, trying to thread the needle, it's a very nuanced and complex conversation. I've seen a lot of headlines conflating the 1.5 degree year we just saw with the 1.5 degree temperature target. They are distinctly different things, and that is both good and bad news depending on the context. Also, it's just an illustration of the fact that we're not ready for a 1.5 degree world, let alone a 2 or 3 degree world. And that is sobering. That really is, from the perspective of a climate scientist. So I think that's mostly what I wanted to cover. California, by the way, in 2023 did not see a record warm year, unlike almost everywhere else on Earth. It was an unusually cold year for the first half of the year in 2023. It did get warmer, and we did have a warmer than average summer, although not an extraordinarily warm summer by any recent standard. The only month that really stood out as being extraordinarily warm, I guess the 2 months, the latter half of November and then December. And that period was the warmest on record in some parts of California, as I mentioned earlier, the Central Coast, the Southern Sierra, and the Central Valley, portions of it. So we did see record warmth in California this year, but it wasn't as sustained or as extreme as almost everywhere else on Earth. I would not expect that luck will continue into 2024. In fact, I think that California may be on track to hit a lot of new temperature records next calendar year, given how warm the oceans are and the seasonal predictions. By the way, I mentioned earlier how there is even less certainty now regarding precipitation in California for the next couple of months. Well, there continues to be high confidence that the rest of winter will be much warmer than average throughout the Southwest, and so that is likely to result in continued poor snowpack conditions. The present notwithstanding, we're going to get a really good week in there now, so I'm hoping that folks can bank as much snowpack as possible in the next 10 days, because the rest of the season doesn't look so great. Even if the rains return to California, as I think they might in February or March, it likely will be more rain than snow. And so that might not really help out the snowpack as much, even though it will help out with reservoir levels, stream flow, things like that. So snow drought remains a distinct possibility, especially across the southern tier of the western U.S. This winter. We certainly have one right now in most places. All right, so I want to go through quickly and take some of these questions. There's not too many, so I'll go through as many as I can. And try to wrap up, make this a true office hour and actually be done within the hour for once. Give my voice a rest. So bear with me for a moment. You may see a brief ad while I read the questions. All right, everybody. Thanks for bearing with me. Some feedback from the event at the museum last week, actually. Thank you for that. I'm glad folks were able to come. Again, there are a few more events in that sequence. I won't be there for those ones, but other folks who you may very well be interested in seeing will be. Yeah, there's a comment from Brody. It's been interesting to follow the recent application of AI models to weather forecasting. It seems like a lot of other situations where they won't necessarily replace what we have currently, but instead maybe be used in conjunction with it. I still want to have a dedicated session at some point talking about AI and weather and climate, because I think there's just this explosion going on in the field, and I think there is both a lot of promise and a lot of overpromise. I think they're both true. I think it will be transformative for the field, but maybe not in the ways that a lot of folks currently implementing it might think at the moment. And so I think that'll be a good conversation. By the way, if folks at tech companies want to talk about that, I've been working with a lot of folks, not on the implementation side, but on the sort of the bigger picture side of that in recent months. It's been kind of overwhelming, honestly, to keep track of the literature. I mean, there's just like it feels like there's a new paper out every single day on this. So I've been trying to drink from that fire hose among others recently. Anyway, good question. That's my very vague answer. But I actually want to have a session where I talk about that in a more dedicated way. So stay tuned. Try and get an interesting guest to join me, perhaps. Let's see. A question from Paul. Is your prediction that the spring-summer is going to be hotter than average based on climate change, or is it El Nino as a factor as well? And what does that change if we rapidly shift to neutral La Nina? You know, the interesting thing, well, the short answer is yes, it's mainly climate change, but it's also that the seasonal models right now are just showing sustained, pretty extreme warmth in California and the West, straight through winter into spring and into next summer right now. And it's actually not the case. El Nino doesn't necessarily lead to warmer summers in California. It does in some of the tropics, but in California, it doesn't necessarily lead to warmer summers. In fact, La Nina can sometimes lead to warmer summers. So if you do that plus climate change, plus whatever the hell is going on with the global oceans right now, all of that together points to the potential for a really warm spring, following a warm winter and followed by perhaps another really warm summer. It doesn't necessarily mean we'll see really individually extreme heat waves, but it does mean that in aggregate the warmth could be record breaking. So we'll cross that bridge when we come a little bit closer to it, I guess. Um, Lauren remarks, "Happy 75th anniversary of the 1949 SoCal snowstorm. Can that be characterized as having been associated with an Arctic air mass that was not modified?" That's a great question. There have been some photos I've seen circulated of like UCLA campus with like solid 3 or 4 inches of snow on the ground. Uh, Kind of remarkable. The short answer is yes. That was really the only way to get cold air that far south near sea level is to have an air mass that is as unmodified as possible. And what that usually means is it has to take a very weird and sometimes circuitous path. You actually need to get cold air that originates over northwestern Canada, so the interior of British Columbia and western Alberta, that pools up there and then moves southwestward, essentially makes the overland trek from southern British Columbia, southern interior British Columbia, again on the east side of the mountains, and stays on the east side of the West Coast Mountains. So dropping southward over western Montana, over the Bitterroots, across the Snake River Plain in Idaho, continued south east of the Cascades in Oregon, and in some cases even east of the Sierra Nevada before sort of spilling southwestward right over Southern California. That's kind of the path. It's really the only path that air can take to result in an Arctic outbreak in Southern California that leads to sea level snowfall. That's why it's so rare. And as the Arctic has gotten warmer, it just means that that pattern has happened again in recent years, but the air mass associated with it just hasn't been quite as cold. And so sea level snow is right at the edge of what was possible at that point in time with a few degrees of winter warming up in the northern latitudes. That might have been just enough to prevent that from happening. So we do occasionally see those kinds of patterns. Just to be clear, we're not seeing that pattern right now by any means. But I hesitate. I'm not sure that it would be possible realistically to see sea level snow in Southern California at this point in our warming climate. I guess never say never. I mean, we've seen some other, extreme cold outbreaks that seem very implausible to impossible in our present climate. But I think the fact that we saw this happen several times, actually, there were widespread snowfall events in San Francisco and Los Angeles in the first half of the 20th century on several occasions. It was never common since the cities so named have been there, at least. But at least it did occasionally, rarely occur every couple of decades or so. But then since about the 1970s, it really hasn't happened in either of those places at all. And I don't think that's a coincidence. It's since the 1970s that the warming trend, both globally and regionally, began in earnest. So, I think that, but to answer the question, yes, that was a remarkable event, and that is exactly the kind of pattern in terms of a almost completely unmodified Arctic air mass that I'm talking about. Had it moved westward over the Pacific, you might have gotten some nice snowfall in the coast ranges, down to 1,000 or 1,500 feet. We saw that last year on a pretty widespread basis, even in Southern California, and sometimes even the upper valleys in interior Southern California, since some of those get up to around 1,000 feet elevation. We also saw that last year in some spots. But to get it down that last 1,000 feet to sea level, where the marine influence is most strong, yeah, that's the way it's got to happen, and it doesn't happen like that really anymore. All right. I'm going to pick 2 or 3 more questions. Okay, I'm going to take two more questions. And these are first, do the Rocky Mountains block cold Canadian air from reaching California? Uh, to a certain extent, yes. In fact, again, for this is always comes as a surprise to at least a few folks. But I live in Boulder, Colorado these days, and that's right along the front range of the Rocky Mountains, meaning that it's just at the base of the foothills on the eastern slopes of the Rockies. To the east is the vast Great Plains of central North America, and to the west, immediately to the west, is the Rocky Mountains themselves. During this Arctic outbreak, it might get down to minus 10, minus 15 degrees here. But if you go just 20 or 30 miles to the west, up into the mountains, it might be above freezing during this event. This is because cold air is very dense. It's like water in a depression. Water doesn't flow uphill, and a cold, dense fluid, whether it's air or anything else, also won't flow against that density gradient. So when there's really cold air over the central United States, it physically doesn't rise in most cases. It's a shallow layer of air generally. It doesn't rise above the mountains themselves, and that's part of the puzzle. The mountains themselves also induce weather patterns that tend to prevent that air from moving back westward. So the prevailing westerlies aloft drive storm track generally from west to east, and the Rocky Mountains themselves can induce on their leeward eastern slopes cyclonic storms that further sort of perpetuate that process. So the mountains themselves are a physical barrier to the movement of air westward. Yes, that's part of it. But they also just tend to they help themselves help generate the weather patterns that move stuff in the air from west to east, generally speaking. The other thing is that in general, California is just right on the ocean. So Western Canada, like the coast of British Columbia, generally doesn't see extreme Arctic outbreaks either, and it's because, again, the wind usually blows from west to east, and you have an ocean which can only get so cold immediately to the west. And so the mountains there, they have some gaps in them, and so you get these localized bursts of Arctic air up there. That's why you do see occasional snowstorms in Vancouver and Seattle and Portland, even though there's places that are close to sea levels, because you have essentially these deep gaps in the mountain ranges that allow that cold air to spill westward. Think of like a gap in the mountains allowing a river to flow through. Well, it's just like that for cold Arctic air sometimes. So in any case, the Rocky Mountains are a key reason why, but it's also because the cold air sources generally exist east of California. So if for some reason there were a big continent to the north of California, or the northwest of California, they could generate really cold air in winter, we might see more cold air events and Arctic air outbreaks. But given the configuration of the continents and the oceans, that is not to be. And the other question I wanted to take before wrapping up today is, let's see. Oh, yes. It was a question from Kate about whether I can talk about this tsunami-like wave that hit the Ventura coast in December, and what conditions lead to those types of waves, and and how they might hit in the future. I want to clarify that I'm not a coastal scientist. I'm not somebody who studies ocean waves. That is a whole field of study. But there's a couple of things I want to point out. One is that tidal levels were really high in general. So the baseline ocean level was really high. Part of that is just due to seasonal variations in astronomical tides. So, the moon and the orbital patterns affect in relatively predictable ways. We know which times of year the highest tides are going to occur. We often, in fact, call those the king tides. And we're having another round of them this week with coastal flooding once again. Those don't themselves have to do with climate change or storms. You can get that on a clear sunny day with no wind and no global warming. You can get really high tide levels just from these variations, these largely predictable variations due to the gravity field, essentially. But on top of that, we also have sea level rise. In many parts of California, the ocean's about a foot higher than it used to be. And in this past week, or in past weeks, including when we had this extreme tsunami-like wave or waves hit various parts of the California coast, we had really, really powerful storms offshore. So these weren't super extreme storms in California, but they were very extreme wind at generating events offshore. It's not always the strongest storms that generate the biggest waves. And this has to do with, I mentioned how the MJO and El Nino need to be in phase. Well, that's actually a different form of wave. That's a horizontal wave rather than a vertical wave in the atmosphere. But it's the same general idea. It's kind of like pushing somebody on a swing. Constructive interference is pushing them at exactly the right moment to make them go higher and higher with each push. You're reinforcing the existing wave pattern of the swing moving back and forth. If you try and push somebody on a moving swing at the wrong moment, that momentum is going to transfer into your hands. You're going to hurt yourself, and you're abruptly going to stop them from swinging. They're going to start swinging with less and less amplitude. So that's destructive interference, whereas pushing them at exactly the right moment would be constructive interference. The same thing can happen with El Nino and the MJO in a horizontal multi-thousand kilometer context. And the same thing can happen with ocean waves. If you have pre-existing waves out there and you have wind coming from a particular speed and direction, you can either start to reinforce the existing waves or destroy them, mitigate them. If you have constructive reinforcement, you can get really big waves. And that's a function of a lot of different things. It's a function of the pre-existing wave pattern. It's a function of the speed and direction of the winds and the duration of the winds. It's a function of the ocean surface conditions themselves. So again, this happened to be a period where the pre-existing tide level was very high due to natural astronomical variations, in an era where we've seen about a foot of sea level rise along parts of the California coast. So essentially, everything is about a foot higher, 8 to 12 inches higher than it used to be. So a rising tide raises all ships, in this case, literally. And so the big waves we were seeing was acting on a higher baseline than we're used to seeing in a long-term context due to global warming and sea level rise, and in a short-term context due to the natural astronomical high tides. They weren't even technically king tides, but they were higher than usual. So all of that together, some of predisposed the area to coastal flooding and inundation, and then on top of that, there probably were some rogue waves involved. So that dramatic footage, and I normally I would hesitate to call it tsunami-like, but I mean, you look at the footage and like people running inland like 5 or 6 blocks as the ocean just fills the streets. It looks a lot like a tsunami and probably had similar impacts as a small to medium-sized tsunami in Ventura. It did cause damage and it did hurt people. Fortunately, nobody died. But people were swept out back into the ocean, and cars were bumping around, and lots of windows were broken, and businesses and homes were flooded. So yeah, it was a significant event. All of that, plus the existence of a quote-unquote rogue wave. So there was one wave on top of all of that was a good 5 or 10 feet higher than every other wave in the sequence. And given the high tides, given the tidal surge, all of that, it was enough to really just wreak a lot of havoc. And similar things I think happened near Santa Cruz, Capitola, and some other parts of the coast as well. So again, not a wave expert, but that's a brief primer on waves in general in the atmosphere and ocean, how they're similar, how they're different, constructive and destructive interference, and how both natural things, natural variations, random good or bad luck, plus not so natural things, long-term changes in sea level, can conspire. We don't notice sea level rise most of the time, by the way. But we sure noticed it when that giant wave made it considerably further inland than it would have had the sea level been a foot lower on average. On the eastern seaboard, as I mentioned at the beginning of the call, they saw record storm surges from a storm that itself wasn't record-breaking, but places flooded that had never flooded before. Some places still would have flooded whether or not there had been sea level rise due to global warming, but some places did flood that would not have flooded were there not sea level rise, and some places that would have flooded anyway flooded more severely and more deeply. And so this is a case where the difference between barely getting an inch or two of water or getting a foot or two of water is actually a pretty significant difference, both in terms of the energy of that moving water and just how much you've got to clean up. So I think I'll leave it with that in this conversation. I'll thank everybody for joining. I'm going to try and have more regular weekly office hours once again now that things are starting to slightly calm down. But again, thanks for joining. You can check out the new blog post. It's still pretty fresh. It's less than 24 hours old. and I'll talk to you all next time.